Hello, everyone. And I'd like to thank the organization, Thunderhead, for putting this together and inviting us. I'm going to talk a little bit. Well, this talk is going to be a bit technical. I'm going to talk a little bit about the work we've been doing on including some further capability than what's on FDS to simulate curvilinear or complex geometries, as we like to talk about these. And I've seen that some of the previous talks, people use curvilinear geometries within what's in FDS and the capability of FDS nowadays. So I hope this is of interest. These are the contents of the talk. I'm going to talk a little bit about the motivation for this. Well, we've seen a little bit on the previous talks, and what are we going to do to address getting our curvilinear geometries and trying to get fidelity in the simulations with them. Mainly, I'm going to talk a little bit about the inner workings or what's under the hood on the FDS model. The scalar transport of the for species, for chemical species, and how that's being dealt in the added software we're working on, and the energy equation and the divergence constraint. Also, these are equations that we need to resolve and solve around our geometries. And the reconstruction for the velocity, the momentum equations, what is it that we propose and we are employing at this point. I'm going to talk very briefly about within this coupling with the momentum equations, there appears and the software, the scheme we use in order to advance them. There is what's called a projection method. I'm going to talk a little bit because there appears a particular equation that needs to be solved. I'm going to talk briefly about that. That's the Poisson Equation, and Susan Killian will talk, I think tomorrow. She's going to talk a little bit more on the work she's been doing within FDS. And I'm going to give some examples. So, well, I guess most of you knows what FDS is and what's used for. Performance-based design, cases we've seen before, forensic work, and lately, at least within NIST, there is the interest of simulating wildland and wildland urban interface scenarios. We've been also, and one of the main reasons that this idea of including a complex geometry scheme within FDS came about was for applications in fire structure interaction, where there can be large deformations of structures, like what we can see on an image there. And the other would be on fire on compartments, where we have just curvilinear geometries, the case of firing cabins, trains, plane cabins, or simply just architecturally complex civil structures. So the idea here is to, try to enhance as an add-on on working with what's already there in FDS as a solver to develop an efficient and conservative method for the treatment of complex geometry within FDS. There are a few equations here. This is mainly what's being solved on the gas phase, from the gas phase standpoint in FDS. On the right, we can see two pictures. We can see two pictures. Mainly what we have planned, and given that, FDS uses these Cartesian meshes in 3 dimensions, a natural way to include complex geometry capability is to use what are called cut cells. What you basically do is you find what's the intersection of your object with curvilinear geometry with the Cartesian grid from FDS. And you have to find all these polyhedra that are left in the gas phase for the intersection. And you have to reformulate your discretizations for the different set of equations that are going to be acting there. We can see on the left here for scalar transport, everything that is related to discretization of advective, diffusive terms has to be modified for that. Combustion and those gas cells would have to be also, the routines would have to be modified to take into account the new volumes that we have, the same as the radiation transport solver. In terms of energy and our thermodynamic divergence equation, this is being used as a proxy for the energy evolution in the model, will have to also be modified because there are terms that are practically related to scalar transport. And also in the projection method for momentum, we would also have to take this into account with the Poisson equation, and also for the projection, and also to reconstruct velocities around these geometries with what's called an immersed boundary method, which is an extension of what's being used now with the rectilinear geometries, OBSTs in FDS. So before we can solve this problem on this new set of cells, or cut cells, in the region close to our complex geometry, we need to find where they are and basically find these polyhedra and compute them and define them. So the first part of the work we've done is defining this computational geometry engine. And the idea is that we are going to define a set of, we want to define a set of cut cell volumes on all the Cartesian cells that are being interfaced by the surface of the object. And we have some requirements for it. We would like to be as robust as possible, to be general, treating as many types of objects as possible, and also to be parallelizable, which means we can use it in computing in parallel mode. And ideally, we'd like it to be efficient in such a way that we can repeat this process at every time step or every set of time steps when we have moving objects. So one of the decisions we took was to use data management through a data structure, where we basically assume that we have two levels of refinement on a mesh. This can be thought as having two levels of refinement on a mesh. The first level is just the basic Cartesian grid in FDS. And within each cell that is being crossed by the boundary, we can have, at a finer level, an arbitrary number of what are called cut cells, these polyhedra. So we have a Cartesian level and then a cut cell level on top of that. And that's what should come out for us in order to do discretization and solve our evolution equations, what should come out from this computational geometry engine. I show you here, first we started working on prototypes in MATLAB for this process. What's being done is a lot of intersections are being computed. We have every plane on our Cartesian grid. We basically have to compute what the intersection of each plane in each direction is with the solid object, and find which are those elements of the intersection, which are basically segments. And they can be triangles if the face of the object is directly aligned on a plane. And we use those we stitch those together in order to form and define which are the faces or the polyhedra on each of the planes that are on the gas side but next to the object. Also, we can use those intersections in order to define faces that lie within our object surface, which we have defined to be a triangulation And the reason for that is mainly because that's like the basic type of mesh that is being used on unstructured finite element methods, for example. And that's those faces those cut faces that are within the surface of the object are also used together with the faces on the planes, and we look at those sets and we figure out which are the volumes, which are these cut cells next to them. We can compute area and volume properties for these, locations of centroids, and this is in order to do the discretization that I'm gonna show next for the equations. Also, we can, what's being shown for this case is we can use, for each of those centroids, we can compute what stencils of points are surrounding those centroids in order to do interpolations. And this is also being used in the immersed boundary method for velocity reconstruction there. So here we have scalar transport. The first equation is just a scalar transport equation. It's just a conservation statement for each of the chemical species. So we have our advective flux, our diffusive fluxes. The diffusive fluxes can be cast in a two-term way, like what we have here. And this is the same equation for each of the species, transport equation for each of the species, and it's put in a format that is easier to discretize when we are using implicit schemes. And I'm going to comment a little bit on that later. So on these equations, in the same way that is done in FDS, we are going to use what's called a finite volume method. So we grab each of our cut cells, each of these polyhedra, and we are going to, well, we compute in an integral sense or in an average sense. Those divergence terms are passed as the computation of fluxes, either advective or diffusive, across the boundaries of our cut cells. And this is one of the schemes that inherently leads to conservation. Conservation means the numerical scheme will not allow, or it will not let mass to be lost or gained. Simply because if you can think of it as one of my colleagues, Randy, would like to think about this, if each of these cells is a bank account, all the money that is coming out from one of these cells is going to go to the next one. And that's basically what this is doing. It's saying whatever mass the flux, specifying the same flux in between cells, is going to basically pin down the conservation, which is the mass is going to be transferred totally. Whatever one loses, the other one gains. Now, these small cut cells that we might end up, because we have a Cartesian, let's say you're running FDS, you have your Cartesian mesh, you put your object there, your immersed object there, and you don't know, you might have cut cells or these polyhedra of different sizes, and some sizes might be really, really small. And people who have used FDS and they increase the number of points or the number of cells in the calculation, they see that the time step becomes smaller. That is because when you integrate these equations in what's called an explicit form, there are stability constraints that have to be met. And the finer the grid, the smaller the time step. Now, if you have very small cells because of this method, you have to deal with them. This is what's called in cut cell methods. This is what's called the small cell problem. So there are alleviation methods for them. In general, you can merge cells in one way or another, or transmit the mass given in one cut cell to its neighbors. The other option that we are exploring is basically solving that region of cut cells and the cells surrounding them in an implicit manner. An implicit manner is a more costly way of integrating, but the good side of that is that these stability issues go away. in a linear sense, they go away. Now, we don't want to solving an implicit problem means that you have to invert a matrix. And the size of the matrix depends on how many of these cells you have. So if we are going to solve this on on the whole mesh, it's going to be very, very expensive. And as we know, our users don't like slow codes, so we are trying to maximize the efficiency of this. And the requirement is only on this region next to the object. So what we do is we solve, as it's done in FDS currently, explicitly, most of the domain. In this region, most of the domain, let's say you have a solid object here, and you solve implicitly close to it, on the region close to it. And what you use is a boundary condition, which is basically, again, specifying advective and diffusive fluxes in this exim boundary, explicit implicit integration boundary, to be the same. We done tests. We're actually, well, some people have done this kind of integration where you solve some part explicitly and some part implicitly. We have done tests, and we've evolved the solver for our particular case, which is combining implicit solvers with the FDS solver, which is a range kata. It's called a range kata method. And in terms of accuracy or time accuracy, at least for heat equations, evolution, we have found good results. How is the work done in the code in order to solve implicitly a region of the domain? Mainly, what you do is you number your unknowns on the implicit region. There's a numbering, and this is essentially has become an unstructured solver on this region. And finite volume methods lend themselves well, or you can be efficient by building either right-hand sides or discretization matrices by faces. So you can build faces lists, which are basically the faces that separate the cells, and then use those in order to compute what the fluxes would be and what the coefficients of these matrices would be for your solution. So, for example, here we have an equation which is an implicit solution. We have a matrix, we have an advection matrix, a diffusion matrix, and this is the evolution equation. This has to be inverted. This advection matrix will change, and in general for LES, which is probably what everyone uses here, the diffusion matrix will also change. So this has to be solved every time step, actually every sub-step. At this point, the solution, we are doing it with a library, which is called an Intel solver library. And we have also the option to solve this part of the domain, the implicit part, actually solve it explicitly by just linking small cells to larger cells that are next to them. So these are two options we are evaluating at this point. The procedure is the same. You build your discretization and your discretization matrices, and in one case you would basically invert a matrix system. This can be very expensive. And in another case, it's just a matrix vector multiplication. The downside of using explicit is that you're expected to have less fidelity because you're assuming that the value of, let's say, for example, concentration of fuel on this cell is going to be the same as the one of the cell next door, which is the one you have linked that cell to. These are details that, well, we've been working on. The other very important part of the model is what do we do with the energy equation. The energy equation, in our case, is the sensible enthalpy evolution equation, is factored into a thermodynamic divergence, and this thermodynamic divergence will basically give us will be the divergence of the flow due to heat that would produce our buoyancy, for example. And we have to discretize each of the terms from that expression. Here I put what the expression is. Looks pretty ugly, but there are all these fluxes, mass fluxes, and and of course heat fluxes and heat production due to combustion, etc. These have to be discretized in a way that is the same as what's been done for the scalars in our case. So we have implemented this discretization on the cut cell region, and we have added combustion on the regular cells surrounding the cut cell region. We are in the process of working on the particular cut cells, and well, radiation is another very important physics unit that needs to be modified here. So we have our thermodynamic divergence, we have the scalars, we have the motion of our chemical species and how they're going to evolve in time. Now, part of the motion of those species is given by velocity and convection. And for that, we need to solve the momentum equations. The way we do it is in a sequence that also involves the reconstruction of the velocity field next to our boundary. This is using what's called direct forcing immersed boundary method. And what we do is we have our velocities that are defined on the faces of the cut cells, and we interpolate those values from values that are outside. We don't solve the momentum equation on those faces because that would again give us problems of time stability and so forth. Those velocities can be flux averaged into the underlying Cartesian cells, the core cell level I was discussing. And we can compute what's called the direct forcing force for that particular cell. And this is, in fact, being used in order to do this advancement of the equations through a projection. We can also compute the thermodynamic divergence, as we said, on the cut cells. And we translate from the set of cut cells that live on this Cartesian cell, this divergence to the cell using a divergent integral equality equivalence argument. Once we are at this point, we can basically solve the problem as is done currently in FDS. And that is, we have a Poisson equation for this projection, and then we project the velocity field to the required thermodynamic divergences. And also, well, in the end, the final velocities on the cut faces can be reconstructed. So this is just a comment. The immersed boundary method in general is a method that has been used or has been developed to work with legacy codes. Legacy codes in general, they are fast codes that use finite difference or finite volume methods in structured grids. And the idea there is to be able to, through a force field, represent an object or a boundary, but at the same time, within the projection, to solve this Poisson equation, use fast solvers. Fast solvers are usually trigonometric solvers. Their solvers are very fast compared to, what are iterative solvers that are used on unstructured grids or the regular tetrahedral grids. So that's how this all came about. The thing is that the solution of the key point here is that the solution of the pressure happens everywhere. It happens in the gas phase, it happens inside the solid, and in the end, in the immersed boundaries, you are only satisfying the pressure boundary conditions approximately. That means that you will end up having penetration issues. Basically, the scalars are going to flow in or out, mainly in, to the solid region. This is something we can avoid at a cost, of course, and that is basically defining our solver on the gas phase and also on the underlying Cartesian cells to our cut cell region, employing the right boundary conditions for pressure there. Now, this transforms the problem in an unstructured problem for pressure. And we have worked with that using, in my case, I've used building a matrix, a discretization matrix. I'm using Paradiso, which is this kind of black box library. And we have also been working with Susan. She will speak about what she's been doing. So I'm going to give you an example. We've done several verification test cases to try to evaluate accuracy on the different parts of this development. This is an example on testing what the method does in terms of conservation of scalars. We have two species. There's a species backgrounds in the domain, and there is a species being fed to the background through a vent. And we have a spherical object here. So the test, well, there are some of the properties here. The test is, okay, do your integration and compute two metrics. One of them is the amount of total mass by integrating in the volume of each of the species. And the other set is, by knowing the flux you are imposing and the fluxes of species on the boundaries, you can integrate it in time, you can know how much you should have in there. Of course, the time integration has to be consistent with the numerical method being used. In this case, the FDS integrator. And this is to give you an idea. Here on this plot, we see mass versus time, which of the species computed as integrated in the volume or integrated in time through fluxes over the boundary. And the difference between the two is what we would expect. It has to be very small in order to see this conservation. Now, if this is done doing an unstructured Poisson solution, if it was a structure, you would see a mass change of the order of a couple of digits there, around, yeah. So, well, I'm showing here just the integration. We are computing divergence. This is an isothermal flow. We are showing just, well, species to the mass fraction concentration in time. And, well, all this has to do with developing the tool and trying to make sure that the tool is accurate, the tool is going to provide fidelity in these calculations with complex geometries. And on the other hand, part of the development is trying to see how you are going to, all those methods you have implemented, how you're going to encapsulate them such that the user can work with them. And this is a propane fire on a train cabin. This is a train cabin provided to us by Fabian Brandstrom from Bombardier. This is not a Bombardier cabin. This is something he modified. But this would give us an idea of what the workflow is, and we can also see where PyroSim would be. So we have our CAD model. It has to be a sanitized set of volumes. We can export from our CAD software in a particular format, CAD format, for example, IGS or STL. Then we have a preprocessor. What's called a preprocessor is a measure what we actually need. I'm not sure if PyroSim has this capability or you're planning on doing that. Mainly, you have a preprocessor that would basically define the triangulation and also the tetrahedra mesh inside of your model. And this can be exported in a format that, well, we either are going to provide a set of scripts that can be used to add the model into your input file, FDS input file, or, well, the PyroSim capability would be able to do that. The rest of the simulation is defined as usual. The model is defined within what's called a geometry object. And these are some preliminary calculations without radiation. This is a single mesh, just to show you as a showcase example. This is a fairly decent grid on a single mesh. We have around 50,000 CAD cell unknowns here. And in this case, we used, instead of implicit, we use explicit time integration with linking. And well, we can basically see the flow, and we can see smoke and HHR distributions in time for this. So this, as you can see, this is also on our side with smoke view. We are also putting together the tools in order to do the visualization, taking into account these geometries. This is future work, more validation and verification for this. We are at the point where we have we have developed quite a bit of the software, and we're working on understanding which are the best. We have several options for each of the particular units to use in the particular units. We have to weed out what we're going to do there, and that's going to be through verification and validation and testing and testing parallelization, testing speeds, etc. And there are two main things to do. One is radiation, and the second is the treatment of particles, which is of importance in suppression, well, using Lagrangian particles. And this is mainly for the project that initiated this, which is basically developed the transfer, information transfer to do two-way coupling and hook the FDS to thermomechanical finite element solvers like what we see in ANSYS here. So, well, I will leave it here. I guess we are in time, and I will take questions. Thank you.
Okay. Do we have questions for Marcos? Mm-hmm.
Hello, Wojciech. That's very impressive work. I'm wondering, because when you implement the castle boundary layer around an object, yes, a bluff body, then this layer is also a kind of a wall layer for the turbulence model. How do you plan on incorporating the LES model with this area? Yes. Thank you.
At this point, what we do with LES is mainly we do interpolation of the turbulent viscosities using Van-Dries damping into the Cartesian, into the underlying Cartesian cells, and that's what's being used in the evolution of momentum. As in every LES calculation, we don't resolve the boundary layer. We cannot afford it, and we haven't done it. I mean, we cannot do it. So the next step, and it's something that we are thinking about, is how that is going to be, or what we have now, which is a more, let's say, complicated version of the boundary conforming case in FDS, how we are going to include also wall models for this, both for velocity and also for thermal.
And have you considered some turbulence models that are hybrid, like implementing some case of runs in the proximity? There,
to my understanding, there's no such a thing on FDS. I know, like the ES you're talking about. This is something we haven't discussed, but yeah, it might be something to consider.
Thank you very much.
Yeah.
You've talked about moving boundaries, and my experience with the immersed solid method with moving boundaries is that pressure against the moving boundary depends highly on mesh on the mesh size.
Yeah.
And it can vary a lot, and especially when you're studying the induced flows, yes, for example, of a train in a tunnel.
Yes.
You can get very large differences. Yes. Have you seen this problem? Do you have a way to solve it?
Yes, and this is a problem not only in moving boundaries, but it's also in stationary boundaries. In general, when you force the velocity field inside the solid, and also you use the reconstruction outside, you might end up with very large divergences. For example, in case of incompressible flow, that will give you spikes in the pressure. In general, what people do to deal with this is they interpolate the value of pressure to those cells before doing an integration to no forces, for example. And this is the plan. But on the other hand, when I'm talking about moving boundaries and interaction, we are not as much interested on hydrodynamic forces as in the thermal degradation under load of the structures.
And also, do you have a roadmap for when this is going to be available in FDS?
Well, the plan is to have something working for the next major release. We expect it's going to be by the end of next year, but that depends on how things go. On the other hand, these are things that we are testing, and there might be. I've seen that many of you have cases that we could try to use to validate our solver. So that will be most welcome. Definitely.
Thank you very much.
Anybody else?
Gerald Grebos. My question concerns the cost in computation time. If you have to solve in each time step in implicit integration,
yes.
Just for maybe a small system of equations, because it's only 5–10% of the cells that are members of this system. Still, how much will it cost or how much will it add to the computation time of a normal system?
Of course, that will depend on the amount of cells you have in the implicit region. If you have a domain where you have a very intricate shape and most of the cells you have in your domain are implicit, is gonna make it very expensive. For example, this case I showed here. In general, and this is using the unstructured Poisson equation. This takes, respect to the trigonometric solver, it would take around 4 or 5 times that particular solve. That increases the time of the whole simulation. It might make it twice. It might make it. So that said, we also have the option. If people are very, is very important the speed, as we know. We also have the option of doing everything explicit and still using the trigonometric solver. That would end up costing just a little bit more, a few percentage points.
Fortunately, most of our structures are rectangular, and we have only some few details where we need this, but there it's really, really needed. Okay, thank you.
Okay. Well, thank you very much, Marcos. Really appreciate the talk.